Okay, I'm expecting 9 people because Joel and Yesu, they're out to attend the conference today. And even Monday, they are going to attend the conference. Oh, no. So maybe one can start here, the other person can do here. I want to see, but you haven't discussed together, right? So it's kind of independent, even if you're using MATLAB. And but if you're ready, you can do. But maybe everybody, I ask everybody to solve. Arlene, you solve problem number 2. Hey, come on, stand up and get out here.
I assume everybody should solve, right? Everybody ready for problem number 2?
Okay, this is just example problem number 2. So, following the FORM, I just follow the every steps and I'm using the method and I obtain the final result. So I will explain my small code. And first, we have to make input data. This is already given the problem. So I input every data in here. L length, D is maximum displacement, Young's modulus, and width and thickness. And this is, we have 2 independent random variables. So using the given data, I'm input in this part. And we have, for flowchart, we have 3 error criteria. So I'm just use my own criteria number. So using this number, I will do iteration. And this is defined array. After calculation, we have to input the number into the array. So n is the maximum iteration number, and u is u space, and beta is reliability index, and g is filtering function. And gg means gradient g, a is unit direction vector. So at first, this full I'm iterate 1 to n. At first, I input the 30, so maximum this subroutine to 30 times. First, we have to transform x space to u space using this way, and we can calculate g and gradient g and norm of g.
Excuse me, so did you try all 30 times or stop right
Yeah.
there?
I'm using the stop criteria, so it should be stopped if the satisfied error criteria. So after that, we have to calculate the unit vector and reliability index 2. And following that, we will iterate u, we make new u. So after that, using the stop criteria. This is the stop criteria as you know that. And after that, we will if subroutine and about the 3 criteria. And after that, we will break if satisfied the error criteria, and we will obtain the probability of failure. Let's see the just very simple problem. So yeah.
But every iteration, did you put out the parameter value?
Yes.
You compare what the professor do.
Yes. Purpose reduce visual. I will compare everything. This is 0.03171. This is smaller than the Deuce paper because using my error criteria, I did 5 times maybe, I remember. Let's see the tree. Error. Let's see the error. Error is easier than okay. It made 6 times iteration. So in the paper, in the example, it's just 3 times. So 1.744. But from that, this is a little bit smaller than. So final result is a little bit different, but the almost quantity is same. So using this way, you can easily make the result. But Professor said to us, explained us if the random variable number is increased, we have to make other, we have to use other function like calculation to norm, calculation to gradient of G, because we cannot input every function using hand, so you have to use other functions.
Okay, problem number 3, I'll start, then you finish. Okay. Example problem number 3. This is the simply supported beam problem. It has a vertical loading. It has a 6 different concentrate load. All of them are the random, and the material property is also random. And the cross-sectional property, the value is also random. And allowable stress is also random. So this kind of the problem I call just the exercise problem. It doesn't happen in the reality. And one of the approach I would recommend in reality is you have to really select the particular important parameter as a random variable. You don't have to make everything random variable, but this problem for 20 random variable, you might have a little bit difficulties. Then you have to really tackle to get that really a little bit problem area for programming. Okay, so it has a 6. So it has a 1, it's a loading 2, 3, 4, 5, 6. It named as a P1, P2, P3, P4, P5. The loading is a good parameter introducing the randomness because it has a fluctuations. So then dimension is random. So this is L1, L2, L3, L4, L5, L6, and this L is the span of the P. This is L, this is just to say L. Everything is the random. All dimension is random. And cross-sectional. So this is like this cross-section. AA cross-section. This is section AA. This is wood. And this bottom plate happen to be the aluminum. Okay? And the dimension is, this is A, and this is a B, and this is C, and this is D. It's all random. But if you face to solve this kind of the problem, I wouldn't set the dimension as random. To make the problem a little bit simpler and more realistic. But loading usually is random because uncertainty is there. And other dimension, the random variable is Young's modulus. Young's modulus of aluminum is random. Young's modulus of wood is random. So how many so far? How many random? This is 6 and 7. There is a 13. 1, 2, 3, 4. 4 cross-sectional. And Young's modulus is 2. So 19 plus one more. One more is allowable stress. S is random. So total 20 random variable. And when I say it's a random variable, two quantities you have to define. Which quantity are they? For assume, of course, this is a normal distribution. 20 quantities, and you have to define two parameters, mean and standard deviation. So you have to define mean and standard deviation. Then you're all set. Okay? So far we learned using the transformation that makes the accuracy of the result quite improving, because you are dealing and you are computing in the U space. U space, the projection, as you look at it, the contour map is all the concentric circle. Okay, this is the problem. Then question is, what's the probability of the failure? Information is given like this. However, you have to define the g function. So g function, so PF, you have to look at always a target, right? Probability such that g, I'm going to just put the x is less than equal to 0. That's the format that we are using it. And the g function, the performance function, gx, as just to trace back, gx is a performance function. Gx. So here in this case, as usual, resistance or strength minus actual stress or actual maximum stress. So I can say S minus sigma. This is actual stress. And this is allowable stress. Of course, S is random variable. The problem, exercise problem number 1, we set equal to like 3 inches. That's a deterministic quantity. Then, of course, we have a mean and standard deviation. And what we know is, if I say x is equal to, x is a whole random variable, right? And this is equal to xi. I is equal to 1 to 20. And if I write here, of course, if I just rewrite, I can say 1, x2, all the way through x20, which is really equivalent to saying that start the P1, right? Start P1, or A, B, C, D. I can write over here, A, B, C, D, then L1, L2, all the way through here is EA, E, wood, then S. So it relates easiest way, or you can just use this notation. So it's all, this guy could be here. Whichever you want to do, you have to designate the x vector. Right? That's what you have to do. And this is one vector, okay? And the maximum stress, where the maximum stress could occur in this situation, at the center, right? This is symmetric loading, and cross-sectional the property that's really uniform. It's not tapered anything. So right at the middle, so around here is maximum stress could occur. What kind of the maximum stress do you anticipate? Bending stress, right? Bending stress, how do you compute the bending stress? William, are you okay? You wake up? So you compute, this is a sophomore mechanics. You compute the reaction force. This is everything symmetry. Reaction force. Then take the moments about that point, right? Right? Then you use what formula? Bending stress is sigma. What equation do you remember? You remember MC over I? Look at me, MC over I, right? MC over I, right? So over here is the moments is right at that point at the middle. Then you can compute the moments by the reaction force, positive. Then this is counterclockwise, negative, negative, negative. And you will compute the bending moments at the center of the beam. Then C, what's the C value? What's the C? C is simply, this is all symmetric, cross-sectional. So where the maximum bending stress occurs, top or bottom, depend on the loading. In these loading situations, it's a downward static loading. So maximum bending stress is a positive, which means it's a tensile loading right here, right? In this surface, right? Right? Then C is the distance from the neutral axis. So this is a C, which is a half of the B. It's a C, over here is a C. And what about the I? Moment of inertia, right? So moment of inertia, I, so M you can compute that, right? M you can compute that. And C is half of the B. And I is, you remember the rectangular cross section? B? Tongtae, you remember? Louder. A multiply, A is a width, right? A is a width here, right? Oh, I'm sorry, here, I made a mistake, it's C. What's wrong for that? Aluminum is there also, right? This half is only for wood. And aluminum, you have to add by the aluminum. About the neutral axis, you have to compute the neutral axis also. Because this is additional plate at the bottom to resist better to tensile stresses. So that you have to modify this, right? And anyway, for the rectangular plate, about the if it's a rectangular plate, BH, as I recall, this is 12, right? Something like that. And if it's like this, right? The moment of inertia about on axis usually very small because depth is the depth is very small. That's what happened here. Then what happened? How do you compute the moment of inertia? Is area, right, times square of this length. So anyway, you have to compute that, right, using basic mechanics and compute the bending stress. But in this course, the purpose is not to compute the bending stress, all that. It gives you already how generous it is. So if you look at the page 21, it give you the bending stress. The bending stress is, of course, functions of all the random variable except the allowable stress S. So, which is a function of x1, x2, everything, x1, x2, all the way through x19, which is in page 21. You take a look at page 21. Usually you have to get the formulation for the bending stress, okay, which is a function of the 19 random variable. Last random variable I set as S, so S happened to be the what? That's allowable stress. So F, the sigma you get, and now you can define the G, performance function or limit state function is the same thing as S minus sigma, allowable minus actual. So for the probability function now you can define as a probability such that S minus sigma has to be less than equal to 0. It's some job to do. So now basic formulation is done. Basic formulation is done. First, what you have to do to make life easier, to transform from X space to the U space. That's the first thing to do. But I'm going to show you starting maybe today or Monday, mean value first order reliability method, which is again approximations are there. So you can say just easy. Easy means there could be more crude, rough approximation in there. If the performance function has a high or higher nonlinearity in there, function is like x cubed, x fourth power, for example, then PF maybe not that great. So estimation quality may be low, vice versa. But anyway, this is what you have here. So transformation is first thing to do before we do anything. Transformation from X space into the U space. And to do that, then we use, as usual, xi minus mu xi sigma xi to be able to use standard normal distribution function in the U space. That's what. So over here, I is equal to all the way through 20. When you do this, then you can just multiply this out, then pull this xi out. So I can say xi is equal to mu xi plus ui. This is u is a random, so you have a 20 the random variable in the u space. So this is what you have. So now if I write x, then of course I'm going to rewrite, and this is xi 1 through 20. So now you have now u. If I just rewrite over here, replace xi to that guy, so I have mu xi plus u I and sigma xi, and of course you have 20. So now you can really change this guy into the u. This is still like this. Now I can claim that u is, there is a ui, I is equal to 1, all the way through 20. Basic relationship is that one. So far good. Or if I can write, if you say something, I can write this guy is equal to xi minus mu xi sigma xi. This is all same thing. This is a transformation from x space to u space. The reason is we want to work on the u space to make life easier. Then we can use all the standard normal distribution function. Okay, so now we are ready to work on the step-by-step procedure to get all the parameters we need. Okay, what is it? So GU, now you have expression for the performance function as a function. This is a function of the u. The mean and standard deviations are known. That's a fixed value for each random variable. So if I rewrite here, U naught, well, this is S minus sigma is equal to I can write this guy saying that S is x20, right? Watch carefully, it's not magic. S20 is the last, I erased the last random variable, x20, and okay. I don't have to put this guy. S20, this is S20, so minus sigma should be there, which is a function of all this, x1, x2, all that is mu x starting 2 plus u2 sigma x2, and next one is like a mu x3 plus u3 sigma x3 up to the mu x19 plus u19 sigma 19. Dilemma is here because the sigma is a function of those, right? And in page 21, the deterministic expression for sigma as a function of A, B, C, D, L1, L2, P1, P2, EA, EW, which is all the formula, final formula, which is nothing but the actual stress situation, right? Actual MC over I. MC over I is what it shows as a sigma in page 21. So now you have to substitute really not in the calculation, then you have to really write the long equation. You're not going to do that. In the MATLAB, you should be able to define the parameters, write the stress equation as is, then each variable A, then you have to use, you have to cast into the U space. This is expression in U space because U1, U2, U3, all that is there. But up to here is you can handle nicely. I don't see any really big problem. So this, you have to write this guy in the U space as mu x20 plus u20 sigma x20, because that's a random variable. Up to here, nothing to confuse. But then, of course, at the beginning, what do? You set the u naught trier vector is all 0. At the beginning, everything starts from the origin. That's no problem. But from B, from 2, you have to compute, you have to get the G U naught. Do you have a problem? No problem. Direct is all the informations all are there, right? All the U20, why I said U2, but you have to put, I start, from here, you should start from mu x1. Continuation. Make sense? It's a little complicated, right? But you can do it. This, you have a problem. This is no problem. This is no problem. Reset OZ. Here is a problem. Next one is, you follow exactly the same path as you have done example 1 and example 2. No, procedure doesn't change. Every iteration you have to go through, but you have to get the gradient at evaluate. This means, to simplify this means is the gradient evaluated at the u0. Evaluated at the u0. So, which is del G. Usually we wrote like this, right? G U U2 U del UN evaluated at U0. The authors, that's a red cover book, that's what you're looking. They just write for simplicity like this. First evaluate the partial differential. First to get the partial differential, then evaluate at the u0, which in this case at first iteration all 0, 0, 0. Same thing, right? G u0 u n. But it's easy to write mathematically. But in the MATLAB, go check it out. This is a gradient. This is a vector, 20 entry vector. Should have a subroutine in the MATLAB. So you need a subroutine or get it from other some subroutine book, mathematical books, and get that gradient calculation subroutine. Or if you can just develop the code itself. Then you have to get this guy. This is the one I call the area you have to overcome. Once you have that, then this is easy, right? Let me get the next step here. If you get that expression, others pretty, you can manage well. So next step is this guy. Next step is norm of this guy. Norm is pretty easy. Square root of a square of each component, add them up all together. This is no problem. Then after that, what's the next step? You will compute A0. Right? Okay, right? So A0, which is equal to unit vector is what you are getting, which is normal to a point. Then you are really trying to get the MP point. That's the whole idea. And delta GU0. So this portion, once you get that, this portion is easy. Make sense? And then what's the next step is what's a beta naught? What's the beta value? Beta naught, which is nothing but u0. Initially this is equal to 0 at the beginning. Then start merging. Then lastly, you got the u1. u1 is equal to minus A0 That's what you did, right? U naught plus G U naught delta G. So where is the a little bit difficulty? Get the subroutine to get the gradient. I don't have, and you are using the MATLAB all the time. You could get 1A another. In all the days, there are tons of algorithm to compute the eigenvalue, eigenvector that Argonne National Lab put out that much thick book to just compile all different algorithms and subroutine to compute the eigenvalues and eigenvector. It was very helpful. In addition, they put the disk. Those days is a small square disk. Have you seen small square disk? Era is different. So then we just download for that one. So you can maybe gradient. Or if anybody can do the write up the code, develop the code, that's fine. One area is in this. Otherwise, you keep iterate, right? Once you do that, keep iterate. That's all I can tell you here, because processes after that is major, just a regular, common routine to compute. Okay, lastly, so as a group, and we have one group here, another group, Songtae, and another group. We have a 4 group over the weekend. I want you to sit down, really discuss. Songtae, well, they're all coming back tonight, then you should get together over the weekend, generate the one problem in your area. Doesn't have to be in your area. If you involve in stock, don't involve in stock in your early stage in your life. You will lose. It's okay in the stock management. Whatever you have an interest in, let it put it that way. And develop, doesn't have to be 20 random variable. It can be 100 random variable if you want. But I don't want that. But more than 2 random variable, okay? If it's 2, that's too simple. Some meaningful number of random variable, and generate the problem as a term project. I want you to present one group at a time. Then we're gonna all help you to define better project if we all can. You follow me? You all follow me. So usually, I don't want to trying to give you a harder time as a saying term project. Term project is, we're going to start next week. You know the procedure. Then you have to develop, you have to compute the probability of the failure. But it's not the final destination. If it's a final destination is to compute the probability of the failure, that's an analysis problem. But I like to see the design problem. Design means you have to set the target probability of the failure. Then you have to get the material type, and you have to get the dimension mostly. Material type. Titanium, oh, it's good, but it's very expensive. And welding, you have to do it in underwater. They're very brittle. All sorts of the things you can think about it and generate some engineering design problem. And start maybe Monday, if anybody ready Monday, then of course I'm keep giving lecture, get the hour that you can really come out, show what you want to do. And that's what I want to do next week. Then you have 2 weeks, right? Then you can turn in the project by 16th of December, that's a Friday. And based on what the design term project would be, then I'll decide the very next week whether giving you final or not. Because final, if you do it, you have to compute the very same things in the same area. You have to compute probability of failure, you have to compute beta, it's all that. So that's what. Yeah. Okay.